following video will show you how to use Simulink, which is a program within MATLAB that can be easily used to model systems and design transfer functions. Simulink is kind of a graphical type programming language, and I'll show you how to build blocks and how to use the program. So begin with MATLAB already open, and you can start Simulink in two different ways. One of the ways is you just click on here on this icon that says Simulink. Alternatively, you can just type Simulink into the command window, and then Simulink starts up. The first thing that you're going to see is this Simulink library browser, and this shows you all of the blocks that you can use to build up your system model. Up here you have the option of opening an existing model or creating a new one, and we will do that right now. So over here you have this sort of model canvas where you can drag blocks from the library browser into the model itself. If you by any chance accidentally close the library browser, you can get it open again by selecting View and then Library Browser. So let's build up a transfer function and then see how Simulink can be used. Within the library browser you have a couple of things. You have here your core Simulink functions, which are the ones that we're going to be focused on. Below you might have a couple of different types of libraries installed that allow you to do different things. For example, there is a system identification toolbox or a video and image processing library, as well as aerospace block set that allows you to model aerodynamic effects onto an airplane. But we won't be focusing on this today. Let's click on the continuous tab, and here you have everything that's kind of related to continuous system models. And since we're going to be using a transfer function in the Laplace domain, this is where we need to be. And then we click a transfer function block and drag it onto our model. Alternatively, you can also right click and select Add to Untitled, or where untitled is our name of the model. So today we want to model a specific transfer function, so double click on the block to bring up its properties, and this you can do with every single block. And then here you can select the numerator coefficients, and these coefficients are the orders of s. So the systems that we want to model in the numerator has s squared plus 6s plus 10. So here we begin with the highest order of s and then kind of go down. And then in the denominator we want to have s cubed plus 0s squared plus 7s and then plus 1. And then here it tells us now the model has been updated and shows us our transfer function. Now since there's not enough space to print it, it just gives it as a numerator of s. However, we can resize the block to actually display and to make sure that the transfer function that we have entered is the same that we want. So now we want to give the system an input and measure its output. Here under the Simulink sinks, you will see all of the places where a signal can end up. You can have things like a display, where you can display in real time the numerical value of a signal, but we don't really want that. We want to actually plot it as a function of time from this scope block. So now what we do, we click onto the out from the transfer function and then drag it over to the scope block, and then it will connect. If for some reason it did not connect, it will stay red. So let's connect our transfer function to the scope block. And then the other thing we want to do, we want to grab a source signal. And the source signal essentially is all the types of signals that you that are source signals. And there's a couple of options. For example, you can select noise blocks. You can just have a constant input. However, what we're interested in is a step input. So then grab it and drag it onto the model. If you double click on the step, you can select a couple of things. You can select the step time, the time at which the step occurs. You can select an initial value, and you can also select a final value. So if your step is 5 in the Laplace, if your transfer function is 5 over s, you can actually select 5 for here. So then you connect it in an open loop way, and then you can actually run and simulate the system. Over here you have the simulation time. So here you can select, for example, now it's going to run for 20 seconds, and then you run it. So now the system has been simulated for 20 seconds. Double click on the scope log to find out what the response to a step input will look like. So here you have it plotted from -5 to 5. If you click on this binoculars icon, which is auto scale, it will show you the output, and you will see that it oscillates unstably out of control. Alright, so now let's use Simulink to design a closed loop system. So we'll have to rearrange a couple of things. You can also rename the blocks, and this is something that would be a very good idea to do, so that you can actually have an idea of what is going on, so that you don't get confused. So here, this transfer function is actually our plant. Changing the name doesn't really do anything other than make it more user-friendly. So here, this commonly used blocks actually combines all of the different types of blocks that are often used from the different tabs. So we are actually interested in having a summation junction. However, since we want to do a negative feedback, we're going to have to change the entries in here. So double click on this summation block, and you'll get the list of signs. Now the list of signs, it begins counterclockwise, and it kind of adds them as you go along. For example, right now it shows you that the top sign is nothing, and then you have 2 positives. If you were to change this to a positive, then you get an extra summation sign. So since we're interested in having a negative feedback loop, let's change the system back to the following configuration, plus minus, and then you get that. Alright, so we want to actually connect this back to here, so we kind of drag it from here and try to park it, with our mouse pointer clicked, try to attach it to the signal. It doesn't always work, sometimes you don't quite get there, so then you have to try to drag it again. Alright, so we run this, and now we have the following type of response. So let's see whether we can kind of manually tune a controller to help us improve the response. So the first thing we're going to do is add a gain block. This allows us to increase our gain in a simple feedback loop. And the gain can be found under commonly used blocks and then gain. Let's delete the signal and then drag the gain block in between. You can also, if you want to quickly connect 2 blocks, you can select the source block and then with Control pressed, select the gain block. And this will directly instantly connect the 2 blocks. And same again, right now we have the gain block selected, and then we click with Control press, we click the plant, and then it instantly connects. So let's rename this to our KP, because this is going to be our proportional gain. And I've previously tuned this controller, so let's try kp is equal to 5. And then let's see what our output is like. So right now our output is the following. However, right now the scope log actually only shows us our actual system output, but we don't know what the step input is or at what time it occurs. So let's use something called a MUX block mux. So we can actually, if you want to detach a block, press shift and then click on the block and then drag it away. What this mux block does, it actually connects two different signals and makes them a vector. So right now we want to have vector output. We want to essentially plot two different things. We want to plot our output as well as our input. So we select our the one of the mux inputs and then drag it off into our step, and you will know that it's properly connected if the signal turns black. If you want to, for example, plot more things at the same time, you can select the number of inputs to 3 or any other number that you want. Alright. One other thing that you can do, you can actually move blocks using the arrow keys, and then if you get close enough to an unconnected signal, Simulink will automatically connect. So now if you run it, you will find that you are actually now plotting two time signals. The first one is your input, and this one just shows you exactly what your step is sending, and the second one is your output. One other thing that you can do with here, with these scope logs, you can actually zoom in on specific areas by clicking anywhere on the canvas and then dragging a box around it, and then you'll see you can kind of have a closer look at what is going on. This is for example useful if you want to actually look and try to find your percent overshoot. Alright, so now let's actually add an integrator into our controller. So in the Simulink library, let's click on continuous and then integrator, and then just drag it on here. And we also want to grab a integral gain. So one thing we can do, we can select a block, press Control, and then drag the block off of there, and then you will see that your mouse pointer changes into a plus. This means that you're going to make a copy. And then when you let go of your left mouse button, it creates a copy and renames it to something else. So here we want KI. So now all we have to do is we have to grab the error. We have to connect all of these blocks. So now we need an additional summation junction in between so that we can add signals from KP and KI. So let's delete this signal and grab a summation block. And one thing we want to do is we want to have this positive point up. So let's change this to the positive and this to not connected, or no block, no signal here. And then just make sure that you connect it properly, because sometimes it defaults to be connected here. So I mean, it doesn't really matter, but just make sure that your signals are connected where you want them to be. Alright, so now when you run it, you'll get the response that has 0 steady state error and has quite a bit of overshoot. So let's add a derivative block. Click on continuous and then grab a derivative block and drag it onto your model. Now the truth is, using a straight up derivative is not really a preferred way whenever you're working with these sort of systems, because whenever you do a step, it'll have an infinite derivative. But let's see what happens when we just try to use it. So let's add an addition here, and then let's add a KD gain, which we'll make 1 for now, and we'll rename this KD. So then again, we can connect all of these. So let's run it and see what happens. So right now it actually worked. However, sometimes you might find that it actually pops up with an error message. So in that, because it says that at some point your derivative happens to be infinite, and Simulink does not like that. So the way you can address this is actually by adding a transfer function to your input. However, the whole purpose of this transfer function is going to be to filter the signal. So if we add the following transfer function in series with your input, you will find, let's run the system, that right now you have your yellow is your input, and you'll find that it's exactly just like a corner. So this particular transfer function has a steady state error of well, it'll just of 0, or for a step input it'll have a 1 output. So if we run this again, we can find that our input is sort of like a corner, but now it's a little bit rounded. This rounding actually allows Simulink to compute a derivative, which will still be pretty high, but it will not be infinity. Alright, so now we run our system and we get the following output, and it's a little bit better. So now you can actually play with these Kp, Ki, and Kd to manually or heuristically tune the system. However, we're not quite done yet. We're sending, we have a controller here, and we're sending some sort of an input into our plant. We actually have to make sure that whatever we're sending is actually something that is feasible for our plant, whether our plant is actually capable of achieving that sort of input. So let's label this input, and then I guess we can also label this C of S. And this signal we can probably also label R of S. Okay, so we've now simulated the system, and now let's look at the input. The input is our U of S, and that's what's being directly sent into the plant. If this was a DC motor, this would be the voltage that the plant would experience. So we get something like this. If we click the auto scale, you'll find that our input suddenly spikes to 100, and that's mainly due to the derivative block. So one thing that we can do is we can physically limit by adding something that's called a saturation. I'm not entirely sure where it is, so I'm going to use the Simulink library browser search function. So here I'm going to type in saturation and then press enter, and then allow Simulink to search for it. So here I can now grab a saturation block and drag it onto our model. If you double click on the saturation, you can actually select upper and lower limits. So let's select 10 or maybe 7 as a practical upper and lower limit. This really depends on your system and should be something that you kind of try and see. So now when you run the system, you still get an output that looks very much like it did before, but now when you click on the input, you'll find that your sudden spike is actually truncated at 7. And the rest of the contributions, you can see that your input is always going to be stay below 1 approximately. So what would happen if our upper limit was larger than, well, if our control input was larger than what our system was capable of handling? If you run this, you will now find that your system response looks quite a lot different, and that's because it actually hits the saturation, and you'll find that this actually limits your controller's ability to respond or to behave properly. So whenever you're designing a controller, you always have to check whether whatever control signal you're sending into your plant is actually feasible and whether you can actually achieve that. All right. So I hope this was a little bit of help, and I hope that this will now get you started with Simulink. Thank you for watching.